All right, so the last piece of our puzzle here is putting our energy and our momentum together. And you hopefully recognize that there must be some connection just based on their equations, since momentum is equal to mass times velocity, and energy, in particular kinetic energy, is equal to 1/2 mv squared. So what you should see here is that our variables that impact these particular values are the same, mass and velocity, but the way in which those variables affect those values are a little bit different. But they are both inherently conserved quantities, or can be conserved quantities given the right situation. So let's look at this interaction between energy and momentum, particularly as it relates to collisions. So we have two specific types of collisions, and I think we've used these terms at some point before and talked about them just in terms of like whether the objects bounce or not. So we have elastic and inelastic collisions. And whether something is deemed an elastic or inelastic collision is more than just whether the object bounces or not. An elastic collision is one where we have conservation of both momentum and kinetic energy. Okay, so momentum and kinetic energy. This type of collision is rare because there are very few collisions where you have a true conservation of kinetic energy. Harder objects actually tend to have more elastic collisions, so like billiard balls or ball bearings, things like that. And the reason for that is because they don't compress. When you have something like a bouncy ball, and if this is our ground, when our ball hits, even though it's probably a very small amount, so here's our perfectly round ball falling, when it hits, this area where the contact is, it compresses, it flattens a little bit. And that compression causes friction between the molecules, it causes a generation of thermal energy, and so you lose kinetic energy. You also have sound that's generated. Sound is energy, and so anytime you have sound, you're losing energy. And so a truly elastic collision needs to be one where there's no compression of the material and there's no sound generated. And the closest thing to that is the interactions of atoms or molecules, particularly gas molecules or ions, as they're flying around and they bounce off of each other. At that level, they're more or less truly elastic collisions. So at the macroscopic level, not really any truly elastic, although there are, just like we ignore friction sometimes because it has such a small effect, there are certainly plenty of situations where we can overlook the kinetic energy lost and just deal with the scenarios as if they were elastic collisions. But in these types of collisions, obviously the masses and initial velocities are something that are determined pre-collision. So you have your masses, they're traveling at some velocity, they collide. And so what we're left with then are just the two velocities. In this situation, our math gets a little bit more complicated because we have two variables and two equations, or two unknown variables and two equations. Maybe, there we go. And it's our conservation of momentum equation, which is that top one, and our conservation of energy equation, of kinetic energy, which is the second one. And this isn't something I'm going to ask you to do, and this isn't something you'll have to do on the AP exam, but I think it's good to at least see that this is a thing that we can do. So we have, and this would obviously be in a two-body system. So we have two objects, M1 and M2. They both have some initial velocity. They elastically collide, and in that collision, the momentum is conserved, which is represented by this piece, and the energy is conserved, the kinetic energy is conserved, which is represented by this piece. And so, using these two equations, you can work through and derive equations for the final velocities of the two objects. And so this equation here is our final velocity of the first object. This equation here is the final velocity of the second object. Again, not something you specifically need to do, but just understand that it can be done. And really the idea here, the big takeaway here is that in an elastic collision, both the kinetic energy and the momentum are conserved. Our Newton's cradles, and I've got the one on my desk, these are pretty good examples of this. So you have these really hard steel ball bearings that we lift and drop, and they hit. And in these collisions, they do make a little bit of sound, right? And there is a little bit of compression, even though it's very small, which is why eventually they stop. But in a good quality one, the back and forth can go for a very long time. And it's in this that we can really see this idea of conservation of momentum and energy as well. So within our Newton's cradle, it really, the idea that both momentum and velocity have to be conserved explains why when we lift one ball up and let it go, one ball comes off the other end. When we lift two balls up, two balls come off at the same speed, not one ball at twice the speed. Because if one ball came off at twice the speed, then we would not have conservation of both kinetic energy and momentum. And so as we do different scenarios with our Newton's cradles, different numbers of balls, the number of balls coming off the other side will always be the same, and the velocity coming off the other side will always be the same. Because you can't change the mass and or the velocity in such a way with this so that both the kinetic energy and the momentum are both conserved. Now, the other type of collision is what we call an inelastic collision. An inelastic is one where we have a loss of kinetic energy. And most of our collisions are what we call partially inelastic. And these are your bouncy balls and your tennis balls bouncing off rackets and golf balls, and really most collisions are partially inelastic. You have a collision, some of the energy gets converted to sound or to thermal energy in the compression or some other type of situation. And a lot of these are the ones that we can estimate or pretend are elastic. And then we have what we call completely inelastic. And these are ones where the objects stick together. And in completely inelastic collisions, that's so carts colliding and sticking together, whether it's with clay or with magnets, or two cars on a road are slammed together and their bumpers stick together, whatever the case may be, where the final mass is the combination of the two initial masses. And in this type of situation, we have the maximum amount of kinetic energy lost. Now that's not necessarily all of it. That's not the full amount of kinetic energy, but it's the maximum amount of kinetic energy. It could be all of it, but not necessarily. Now, how is it possible that you could have all of this kinetic energy lost, but still have momentum being conserved? And the key here is in the type of quantity that each of these is. Energy, remember, is scalar, while momentum is a vector. The best example of this, and where we can very clearly see this, is if we have two carts of equal mass traveling towards each other at the same speed. So in this case, both of those carts have some kinetic energy, and so the total energy of the system is double whatever it is for one cart, because we add the two carts together, and so it's 2 times the KE of one cart. That gives us the total kinetic energy of the system. The momentum of that system, though, if they're moving towards each other, even though each individual cart has some momentum, the total momentum of the system is 0. And so as they move towards each other, they collide, they crash into each other, and they stop. In that stopping, both carts have lost all of their kinetic energy, because now they've both stopped, so there's no velocity. And now both carts still have the same total momentum within the system, which in that case was 0. So it can be a little bit tricky, be careful with that, but within our inelastic collisions, where objects stick together, you can have the kinetic energy lost, and in partially inelastic as well, but the momentum is still conserved, even though they both rely on mass and velocity. Because momentum is a vector, kinetic energy is a scalar.